Geothermal energy. Harnessing the Earth's heat. Course content. Introduction to geothermal energy. The science behind geothermal energy. Geothermal resources and their classification. Exploration and assessment of geothermal sites. Technologies for geothermal energy extraction. Geothermal power plants. Direct use applications of geothermal energy. Environmental impact and sustainability. Economic and policy aspects. Geothermal energy around the world. Part 1. Introduction to geothermal energy. What is geothermal energy? Geothermal energy is the heat stored beneath the Earth's surface. It originates from the planet's formation, radioactive decay of minerals, and the continuous flow of heat from the Earth's core to its surface. This energy can be harnessed for electricity generation, direct heating, and various industrial processes. Unlike solar or wind energy, which are variable and weather-dependent, geothermal energy offers a reliable, constant source of renewable power. It is available 24/7 and has a significantly smaller land footprint compared to other energy sources. Brief history of geothermal use. Humans have used geothermal energy for thousands of years. Early civilizations, including those in China, Rome, and the Americas, utilized hot springs for bathing, cooking, and therapeutic purposes. The first industrial use of geothermal energy occurred in the early 19th century in Italy, where geothermal steam was used to extract boric acid. The first geothermal power plant was built in Larderello, Italy, in 1904. Since then, the technology has evolved significantly, and geothermal energy has become an important component of the renewable energy mix in several countries. Importance of geothermal energy in the modern world. With the global demand for clean and sustainable energy increasing, geothermal energy presents a valuable solution. It contributes to reducing greenhouse gas emissions by replacing fossil fuels, enhancing energy security by diversifying energy sources, providing base load power that complements intermittent renewables, supporting local economies through job creation and local development. Geothermal energy is particularly important for countries located along tectonic plate boundaries, where heat flow from the Earth's interior is more accessible. Key characteristics of geothermal energy. Renewable. The Earth constantly produces heat, making geothermal a long-term energy source. Sustainable. With proper management, geothermal reservoirs can provide energy for decades. Low emissions. Geothermal systems emit little to no greenhouse gases. Base load capability. Unlike solar or wind, geothermal provides consistent round-the-clock power. Global potential and utilization. Globally, geothermal energy remains underutilized despite its vast potential. Countries like the United States, Iceland, the Philippines, Indonesia, and Kenya have made significant progress in exploiting geothermal resources. According to the International Renewable Energy Agency, IRENA, the global installed capacity of geothermal power is over 15 gigawatts, with a large share still untapped. In addition to electricity, direct use of geothermal energy, such as heating buildings, greenhouses, and aquaculture, provides substantial energy savings and environmental benefits. Part 2. The science behind geothermal energy. The Earth's internal structure. To understand geothermal energy, it's essential to grasp the composition and thermal dynamics of the Earth. Crust, the Earth's outermost layer where geothermal energy is most accessible. It ranges from 5 to 70 kilometers thick. Mantle, located beneath the crust, the mantle contains hot, semi-solid rock that transfers heat toward the surface. Core, divided into a liquid outer core and a solid inner core. The core generates heat through the decay of radioactive elements and residual heat from the planet's formation. This internal heat gradually migrates to the Earth's surface, creating the geothermal energy we harness today. Sources of geothermal heat. Geothermal heat originates from three primary sources. Primordial heat, residual heat from the Earth's formation over 4.5 billion years ago. Radioactive decay, heat produced by the decay of isotopes like uranium-238, thorium-232, and potassium-40 within the Earth's interior. Tectonic activity, movement of tectonic plates can cause friction, pressure, and magma intrusion, all of which increase localized geothermal heat. Geothermal gradients. The geothermal gradient is the rate at which temperature increases with depth beneath the Earth's surface. On average, this gradient is about 25 to 30 degrees Celsius per kilometer. However, in tectonically active regions, the gradient can be much higher, making geothermal energy more accessible and economical. Types of geothermal reservoirs. Geothermal resources are categorized based on temperature and accessibility. High-temperature reservoirs, greater than 180 degrees Celsius, typically used for electricity generation, found near active volcanic areas and tectonic plate boundaries. Medium-temperature reservoirs, 100 to 180 degrees Celsius, suitable for electricity generation using binary cycle systems and direct heating. Low-temperature reservoirs, less than 100 degrees Celsius, used mainly for direct heating applications like space heating and greenhouse farming. Hydrothermal systems. Hydrothermal systems, the most common type of geothermal resource, involve the movement of heated water or steam through porous rock formations. These systems are classified into vapor-dominated systems, produce dry steam that can directly drive turbines, e.g. the geysers USA. Liquid-dominated systems contain hot water that can be flashed into steam for power generation. Enhanced geothermal systems, EGS. EGS involves creating artificial geothermal reservoirs by injecting water into hot, dry rock formations that lack natural permeability. This technique allows geothermal energy extraction in areas without conventional hydrothermal resources, significantly expanding the potential of geothermal energy. Heat transfer mechanisms. Geothermal energy involves the transfer of heat via conduction. Heat moves through solid rock due to temperature gradients. Convection. Heat is transferred by the movement of hot fluids, water or steam within the Earth's crust. Advection. Heat carried by fluid movement from deeper to shallower regions. These mechanisms enable the extraction of heat from underground sources for practical use. Part 3. Geothermal resources and their classification. Overview of geothermal resources. Geothermal resources are natural concentrations of heat within the Earth's crust that can be tapped for human use. These resources vary widely in temperature, depth, and physical state, steam, water, or rock. Understanding the types and classifications of geothermal resources helps determine their suitable applications, whether for electricity generation or direct use. Classification by temperature. Geothermal resources are often classified based on the temperature of the geothermal fluid. Low-temperature resources, less than 100 degrees Celsius, suitable for direct use applications such as space heating, aquaculture, and industrial processes. Medium-temperature resources, 100 to 180 degrees Celsius, can be used in binary cycle power plants or direct heating systems. High-temperature resources, greater than 180 degrees Celsius, ideal for electricity generation using dry steam or flash steam technologies. Classification by physical state. Geothermal systems can also be categorized based on the physical state of the geothermal fluid. Dry steam systems contain steam with little or no water. The steam is piped directly to turbines. Example, the geysers in California. Wet steam, hot water systems contain hot water under pressure that flashes into steam when pressure is reduced. Hot dry rock, HDR, systems involve rock at high temperatures but low permeability and little or no water. Water is injected to extract heat. Magma-based systems, theoretical, extremely high-temperature systems located near or above magma chambers. Still under research and not yet commercially viable. Classification by resource type. Hydrothermal resources. These are naturally occurring reservoirs of hot water or steam. They are the most commonly used geothermal resources today. Convective hydrothermal systems. Heat is transported by natural circulation of water. Conductive hydrothermal systems. Heat is transferred by conduction, usually found in less permeable rocks. Geopressured resources. Found in deep sedimentary basins, these resources include hot brine under high pressure, often containing dissolved natural gas. They offer a combination of thermal, mechanical, and chemical energy. Enhanced geothermal systems, EGS. Also called engineered systems, EGS involve artificially creating or enhancing permeability in hot, dry rock formations by injecting water to create a heat exchange system. Supercritical resources. Located at depths where water exists in a supercritical state, between liquid and gas, these resources can potentially yield much higher energy output, but require advanced technology to harness. Classification by use. Geothermal resources are further classified by how they are used. Electricity generation requires high to medium temperature geothermal resources. Direct use applications include district heating, greenhouse farming, aquaculture, industrial heating, and bathing. Ground source heat pumps, GSHP, use the relatively constant temperature of shallow ground, 10 to 15 degrees Celsius, for heating and cooling buildings. Geographical distribution of resources. Geothermal resources are not evenly distributed. They are more abundant in regions with active tectonics, such as the Ring of Fire in the Pacific Basin, Indonesia, Philippines, Japan, etc. The East African Rift Valley, Iceland, and parts of Europe. The Western United States, New Zealand. Regions with volcanic and tectonic activity provide easier access to high-temperature resources. Part 4. Exploration and Assessment of Geothermal Sites. Introduction. Exploring and assessing geothermal sites is the foundation of a successful geothermal energy project. This process involves identifying locations with potential geothermal resources, understanding subsurface characteristics, and evaluating the feasibility of energy extraction. Exploration reduces uncertainty and guides investment decisions. Stages of geothermal exploration. Geothermal site exploration typically follows a phased approach. Preliminary survey, desk study. Objective: identify promising regions using existing geological and geophysical data. Activities: review geological maps and fault data. Analyze regional heat flow studies. Use satellite imagery to detect surface features, e.g. hot springs, fumaroles. Gather historical exploration or drilling data. 2. Surface exploration. Objective: validate and refine preliminary findings through field surveys. Techniques: geological surveys. Identify surface features like hot springs, altered rocks, and fault systems. Geochemical surveys. Analyze the chemical composition of thermal fluids to estimate subsurface temperatures and fluid pathways. Geophysical surveys. Use methods like magnetotellurics, resistivity, seismic reflection, and gravity surveys to map subsurface structures and heat anomalies. 3. Exploratory drilling. Objective: confirm the presence, temperature, and characteristics of geothermal resources. Activities: drill slim holes or shallow wells. Measure temperature gradients. Collect core samples and fluid data. Conduct well logging, e.g., temperature, pressure, and permeability. 4. Reservoir assessment. Objective: evaluate the size, temperature, productivity, and sustainability of the reservoir. Activities: perform flow tests to measure capacity. Model reservoir behavior using simulation software. Estimate long-term yield and sustainability. Assess risks and environmental impacts. Exploration technologies and tools. Infrared imaging. Detect surface heat anomalies using drones or satellite sensors. Resistivity imaging, MT and TEM. Identify zones with high fluid content or clay alteration. Seismic surveys. Map fault lines and fractures that guide geothermal fluid flow. Gravity and magnetic surveys. Locate dense rock formations or magma chambers. Key indicators of geothermal potential. Several surface and subsurface indicators help identify geothermal prospects. Surface manifestations, e.g. geysers, fumaroles, hot springs. High heat flow values. Active fault zones. Geochemical anomalies, e.g. high silica, chloride, or boron content. Elevated geothermal gradients. Risk and uncertainty in exploration. Exploration carries significant financial and technical risks due to subsurface uncertainties. Major challenges include inaccurate prediction of reservoir size or productivity, unexpected geological formations, high drilling costs with no guaranteed success, environmental and social constraints. Mitigating these risks requires thorough, multidisciplinary assessment and often the use of insurance or government incentives. Site selection criteria. A viable geothermal site typically meets the following criteria: adequate heat source, temperature and flow, suitable permeability and porosity of reservoir rocks, availability of water, natural or injected, proximity to transmission infrastructure, minimal environmental and social impact, regulatory and land access support. Part 5. Technologies for geothermal energy extraction. Introduction. The efficient extraction of geothermal energy relies on various technologies that adapt to different resource types, temperatures, and geological conditions. These technologies are critical for converting subsurface heat into usable energy, whether for generating electricity or for direct use applications. This part explores the major extraction technologies and their applications. Well drilling and completion. Drilling geothermal wells is one of the most capital-intensive stages of development, similar to oil and gas drilling, but adapted for high temperatures and corrosive fluids. Key considerations. Depth ranges from a few hundred meters to over 3,000 meters, depending on the resource. Casing and cementing protects the well from collapse and isolates different geological layers. Well design must handle high pressure, temperature, and chemical corrosion. Types of wells. Production wells bring hot fluids or steam to the surface. Injection wells return cooled water to the reservoir to maintain pressure and sustainability. Monitoring wells track pressure, temperature, and chemical changes in the reservoir. Geothermal power plant technologies. There are three main types of geothermal power plants, chosen based on the temperature and pressure of the geothermal resource. 1. Dry steam plants. Application: high-temperature, vapor-dominated resources. Process: steam from the reservoir is piped directly to turbines to generate electricity. Example: the geysers in California, USA. 2. Flash steam plants. Application: liquid-dominated reservoirs greater than 180 degrees Celsius. Process: high-pressure hot water is flashed into steam by reducing pressure. The steam drives turbines. Variants: single flash and double flash systems for efficiency improvement. 3. Binary cycle plants. Application: medium temperature resources, 100 to 180 degrees Celsius. Process: geothermal fluid heats a secondary fluid, e.g. isobutane, with a lower boiling point in a heat exchanger. The vaporized secondary fluid spins the turbine. Advantages: closed-loop system with zero emissions, suitable for low to medium-grade resources. Direct use technologies. Geothermal heat can be used directly without conversion to electricity. These systems are simpler, more efficient, and economical. Examples: district heating systems, greenhouse and soil heating, aquaculture, industrial applications, drying, pasteurization, etc., balneology and spa use. Advantages: lower operational costs, high efficiency, up to 90%. Immediate local benefits. Ground source heat pumps, GSHPs. GSHPs use the stable temperature of shallow ground to provide space heating and cooling. They are suitable even in areas without high-temperature geothermal resources. Working principle. A closed-loop system circulates a fluid through buried pipes. In winter, heat is absorbed from the ground and transferred indoors. In summer, the process is reversed to cool the building. Types: horizontal and vertical closed-loop systems. Open-loop systems using groundwater. Enhanced geothermal systems, EGS. EGS technologies expand geothermal potential by creating artificial reservoirs in hot, impermeable rock formations. Process: drill into hot, dry rock. Inject water at high pressure to create fractures. Circulate water to absorb heat and return it to the surface for energy use. Benefits: access to deep, previously untapped geothermal energy. Potential for global application beyond tectonically active regions. Challenges: high cost and technical complexity. Induced seismicity risks. Need for robust monitoring systems. Innovations in geothermal technology. Recent advancements are pushing the frontiers of geothermal energy. Directional and horizontal drilling increases well productivity and access to wider reservoirs. Supercritical geothermal, targeting fluids above 374 degrees Celsius and 220 bars, which offer 5 to 10 times more energy output. Closed-loop systems eliminate direct contact with rock formations, reducing environmental risk. Hybrid systems combine geothermal with solar or biomass for improved efficiency and reliability. Part 6. Geothermal power plants. Introduction. Geothermal power plants convert underground heat into electricity using steam or hot water drawn from geothermal reservoirs. The choice of power plant technology depends on the temperature, pressure, and composition of the geothermal resource. This part delves into the types of geothermal power plants, their components, and how they operate. Types of geothermal power plants. 1. Dry steam power plants. Application: high temperature, vapor-dominated fields greater than 235 degrees Celsius. Working principle: steam extracted directly from underground is sent to turbines which drive generators. Advantages: simple design, high efficiency, minimal fluid handling. Example: the Geysers geothermal field in California, USA. 2. Flash steam power plants. Application: liquid-dominated resources with temperatures above 180 degrees Celsius. Working principle: high-pressure hot water is brought to the surface. When pressure is reduced, the water flashes into steam. The steam drives turbines, while remaining liquid is either re-injected or flashed again in double flash systems. Variants: single flash, 1 stage of pressure drop. Double flash, 2 pressure drops, improving efficiency. Advantages: widely applicable, relatively high efficiency. 3. Binary cycle power plants. Application: moderate temperature resources, 100 degrees Celsius to 180 degrees Celsius. Working principle: geothermal fluid transfers its heat to a secondary working fluid, e.g., isobutane, pentane, via a heat exchanger. The working fluid vaporizes at low temperatures and drives a turbine. Closed-loop system: both fluids are recirculated. Advantages: low emissions, and minimal environmental impact. Ideal for widespread use with lower temperature resources. Disadvantages: slightly lower efficiency compared to steam plants. Major components of a geothermal power plant. Production wells bring hot fluids to the surface. Turbines convert kinetic energy of steam or vapor into mechanical energy. Generators convert mechanical energy into electricity. Heat exchangers in binary plants transfer heat between fluids. Condensers cool steam back into water for reuse or reinjection. Cooling systems maintain operational temperatures, air or water cool. Injection wells return cooled fluid back into the reservoir to sustain pressure. Operational efficiency and output. Efficiency in geothermal plants is typically lower than in fossil fuel plants, ranging between 10 to 17%, due to lower fluid temperatures. However, their capacity factor, a measure of how often a plant runs at full power, is often over 90%, much higher than wind or solar. Environmental considerations. Geothermal power plants have a small environmental footprint but must manage gaseous emissions, primarily carbon dioxide and trace gases like hydrogen sulfide, though significantly lower than fossil fuels. Surface subsidence, caused by pressure reduction if not managed by reinjection. Water use and contamination, especially in flash systems if waste brine is not handled properly. Induced seismicity in EGS or high-pressure reinjection operations. Examples of geothermal power plants around the world. The Geysers, USA, the world's largest geothermal field with over 1.5 gigawatts capacity. Hellishay Power Station, Iceland, a combined heat and power plant producing 303 megawatts of electricity and 133 megawatts of hot water. Macban and Tiwa Geothermal Complex, Philippines, major contributors to the country's renewable energy portfolio. Olkaria Geothermal Plants, Kenya, a flagship for geothermal development in Africa with significant installed capacity. Hybrid and advanced geothermal plants. Hybrid geothermal solar plants combine thermal energy with solar PV or solar thermal to optimize output. Carbon dioxide plume geothermal, CPG, uses supercritical carbon dioxide as the working fluid to improve efficiency. Geothermal with energy storage, coupling geothermal with battery storage or hydrogen production for grid flexibility. Part 7. Direct use applications of geothermal energy. Introduction. Direct use of geothermal energy refers to utilizing geothermal heat without converting it to electricity. This approach is among the oldest and most efficient ways of harnessing geothermal energy. It is cost-effective, environmentally friendly, and widely used in many parts of the world for heating, industrial, and agricultural purposes. Benefits of direct use. High efficiency, utilizes up to 90% of the available energy. Cost-effective, lower installation and operating costs compared to electricity generation. Low emissions, minimal greenhouse gas emissions and pollutants. Local energy security, reduces dependence on fossil fuels, especially for remote or cold regions. Common applications. 1. District heating. Description: centralized geothermal plants supply hot water or steam through pipelines to heat buildings in towns or cities. Examples: Reykjavik, Iceland, over 90% of buildings are heated using geothermal energy. Boise, Idaho, USA, one of the oldest geothermal district heating systems in North America. 2. Greenhouse heating. Description: geothermal heat maintains optimal temperatures for plant growth, increasing productivity and enabling year-round cultivation. Benefits: stable temperatures, reduced heating costs, environmentally sustainable farming. 3. Aquaculture. Description: geothermal energy heats water in fish farms to promote faster growth and maintain species-specific conditions. Examples: raising catfish, tilapia, trout, and ornamental fish in the USA, China, and Italy. 4. Industrial applications. Description: geothermal heat is used in food drying, pasteurization, milk processing, and mineral extraction. Examples: fruit and vegetable drying in Turkey and China, timber drying and cement curing in Iceland and New Zealand. 5. Bathing and balneology. Description: use of geothermal hot springs and spas for therapeutic and recreational purposes. Cultural and economic value. Major tourist attractions in countries like Japan, onsen, Hungary, and Turkey. Agricultural applications. Geothermal energy supports multiple agricultural activities beyond greenhouse heating. Soil warming accelerates germination and plant growth. Sterilization, used to control soil-borne diseases and pests. Dehydration, low-temperature drying of fruits, vegetables, herbs, and grains. Snow melting and de-icing. Description: geothermal systems circulate hot water through pipes beneath sidewalks, driveways, and roads to prevent ice and snow accumulation. Locations: common in colder climates such as Iceland, Japan, and some areas in the United States. Geothermal heat pumps, GHPs. Though not a direct use of high-temperature geothermal resources, GHPs are highly efficient systems that use shallow ground heat for space heating and cooling. Advantages: year-round operation, lower utility bills, quiet and low-maintenance systems. Common uses: homes, schools, office buildings, and commercial centers. Global examples of direct use. Iceland, leaders in direct use with geothermal heating, greenhouses, spas, and snow melting. Turkey, extensive use in agriculture, aquaculture, and greenhouse heating. China, rapid expansion in geothermal district heating and aquaculture. Kenya, emerging use in greenhouse farming and milk pasteurization. Future trends and opportunities. Integration with sustainable agriculture, supporting vertical farming and hydroponics. Geothermal-based industrial parks, where heat-intensive industries cluster around geothermal sources. Rural electrification and heating, using low-enthalpy resources to support off-grid communities. Part 8. Environmental and social impacts of geothermal energy. Introduction. Geothermal energy is widely regarded as a clean and sustainable energy source. However, like all energy systems, it has environmental and social implications that must be carefully managed. This part explores the various environmental and social impacts of geothermal energy development and outlines strategies for mitigation and responsible management. Environmental impacts. 1. Land use and habitat disturbance. Impact: construction of geothermal power plants, roads, and drilling infrastructure can disturb ecosystems and alter landscapes. Extent: generally smaller than other energy sources like hydropower or fossil fuels. Mitigation: use of existing roads and infrastructure. Compact plant design. Reclamation and restoration post-construction. 2. Water usage and contamination. Impact: water is used for drilling and cooling. In some cases, geothermal fluids contain heavy metals and toxic substances. Risks: groundwater contamination from leaks or spills. Over-extraction of water from local sources. Mitigation: re-injection of geothermal fluids. Closed-loop systems to prevent contamination. Careful monitoring and regulation. 3. Air emissions. Impact: geothermal plants can emit trace gases such as carbon dioxide, hydrogen sulfide, methane, carbon tetrahydride, and ammonia nitrogen trihydride. Comparison: emissions are significantly lower than fossil fuel plants. Mitigation: gas scrubbing systems. Re-injection of non-condensable gases. Use of binary cycle plants with zero emissions. 4. Induced seismicity. Impact: enhanced geothermal systems, EGS, and deep well reinjection can trigger small-scale earthquakes. Examples: notable cases in Switzerland and South Korea. Mitigation: real-time seismic monitoring, controlled fluid injection rates, avoidance of fault zones. 5. Subsidence. Impact: excessive withdrawal of geothermal fluids without reinjection can lead to ground subsidence. Consequences: structural damage, changes in topography. Mitigation: balanced reinjection, careful reservoir pressure management. Social impacts. 1. Community engagement and acceptance. Impact: local populations may resist geothermal projects due to land use, cultural concerns, or lack of involvement. Mitigation: early and transparent consultation, community benefit sharing, incorporation of local knowledge in planning. 2. Land rights and indigenous issues. Impact: projects may infringe on indigenous lands or sacred sites. Mitigation: free, prior, and informed consent (FPIC), respect for traditional practices and heritage, inclusive decision-making processes. 3. Job creation and economic development. Positive impact: geothermal projects generate employment in construction, operations, and maintenance. Long-term benefits: skills development, local business stimulation, access to clean energy for rural communities, regulatory and environmental compliance. Geothermal projects must comply with national and international environmental standards, including environmental impact assessments, EIAs, permitting and licensing, water use and emission regulations, monitoring and reporting requirements. International organizations such as the International Geothermal Association, IGA, and World Bank promote best practices in environmental stewardship. Life cycle assessment, LCA, of geothermal energy. Carbon footprint: geothermal energy has one of the lowest life cycle emissions among energy sources, typically 38 to 79 grams carbon dioxide per kilowatt-hour. Material use involves steel, concrete, and drilling fluids. Materials are mostly recyclable or manageable. Waste generation includes scale, brine, and gases, all of which can be treated or reinjected. Sustainability and best practices. To ensure the long-term sustainability of geothermal resources, best practices include reinjection of fluids, maintains reservoir pressure and avoids depletion. Reservoir management, continuous monitoring and modeling to prevent overuse. Integrated resource planning, balancing energy generation with ecological and social factors. Case studies. Iceland: strong regulatory framework and public support ensure sustainable and community-friendly geothermal development. Kenya: Olkaria: extensive efforts to relocate and compensate Maasai communities affected by geothermal expansion. Philippines: community benefit sharing models and environmental programs tied to geothermal projects. Part 9. Economics and financing of geothermal energy projects. Introduction. While geothermal energy offers long-term economic and environmental benefits, the upfront capital and development risks can be substantial. Understanding the economic landscape and financing mechanisms is crucial for successful geothermal project implementation. This part explores cost structures, investment risks, financial models, and global examples of project financing. Cost structure of geothermal projects. Geothermal energy has a unique cost profile compared to other renewable sources due to its exploration and drilling requirements. 1. Capital costs. Typically 60 to 80% of total project costs. Includes exploration, geological surveys, test drilling, well drilling and completion, surface facilities, power plant, pipelines, transmission. 2. Operational and maintenance (O&M) costs. Relatively low and stable. Includes plant operations, routine maintenance, monitoring, and reinjection. 3. Levelized cost of electricity, LCOE. Global average, $50 to $80 per megawatt-hour. Competitive with fossil fuels and other renewables, especially over the long term. High capacity factor, greater than 90%, lowers the LCOE compared to solar and wind. Exploration and drilling risks. Exploration carries significant financial risk due to the uncertainty in resource availability and quality. Key risks. Resource risk, uncertainty about temperature, pressure, and flow rate. Drilling failure, dry or non-productive wells. Regulatory delays, permitting and compliance hurdles. Risk mitigation strategies. Government-backed drilling programs. Insurance for exploration. Detailed geological surveys and feasibility studies. Financing models. Several models exist to fund geothermal projects, often requiring public-private collaboration. 1. Public financing. Government grants, subsidies, and tax incentives. Support for early-stage exploration. Examples: feed-in tariffs, Germany; renewable energy development funds, Indonesia. 2. Private investment. Equity financing from private developers or investors. Loans from commercial banks. Corporate power purchase agreements, PPAs. 3. Multilateral and development banks. Institutions like the World Bank, Asian Development Bank, ADB, and African Development Bank, AFDB, provide concessional loans, guarantees, technical assistance. 4. Public-private partnerships, PPPs. Shared investment and risk between government and private firms. Encourages technology transfer and local capacity building. Investment incentives and policies. Governments can catalyze geothermal development by offering feed-in tariffs, FITs, guaranteed prices for geothermal electricity. Renewable energy credits, RECs, tradable certificates for clean energy production. Tax breaks and accelerated depreciation, reduce upfront tax burden. Exploration risk mitigation funds, provide insurance or cover for failed wells. Case studies in financing. 1. Kenya, Olkaria Geothermal Project. Financed by a mix of public funds, international donors, e.g. JICA, World Bank, and private companies. Government ownership through KenGen with independent power producers, IPPs. 2. Indonesia, Sarula Geothermal Plant. One of the world's largest geothermal plants. Financed through a consortium of multinational banks and development institutions. 3. Turkey, Geothermal Feed-in Tariff Program. Government-backed FIT attracted private investments. Rapid expansion of small and medium-sized geothermal projects. Economic co-benefits. Job creation, skilled and unskilled jobs during construction and operation. Local development, infrastructure upgrades and energy access. Export potential, countries with strong geothermal industries, e.g. Iceland, Philippines, export expertise and equipment. Challenges in financing. High upfront costs, barrier for small or developing countries. Long payback periods may deter private investors. Lack of risk mitigation instruments, particularly in early-stage exploration. Currency and political risk in foreign-funded projects. Strategies for improving investment climate. Strengthen regulatory frameworks. Promote regional cooperation and shared infrastructure. Encourage blended finance and green bonds. Support research and demonstration projects. Part 10. Global Geothermal Energy Market and Future Outlook. Introduction. Geothermal energy is gaining increasing attention as a reliable, low-carbon energy source that can contribute to global energy security and climate goals. While it remains underutilized compared to other renewables, the global geothermal market is poised for growth driven by technology innovation, supportive policies, and rising demand for clean energy. Current global market status. 1. Installed capacity. As of 2024, global geothermal electricity generation capacity exceeds 16 gigawatts, spread across more than 30 countries. Top producers: USA -3.7 gigawatts, Indonesia -2.8 gigawatts, Philippines -1.9 gigawatts, Turkey -1.7 gigawatts, Kenya -950 megawatts. 2. Direct use applications. Used in over 80 countries for district heating, greenhouses, aquaculture, industrial processes, and bathing. Leading countries include China, largest for direct use. Iceland, almost 90% of homes heated by geothermal. Turkey and Hungary, major use in agriculture. Market drivers: climate change mitigation, demand for low-emission baseload energy. Energy security, reduces reliance on imported fossil fuels. Technological advancements, enhanced geothermal systems, EGS, low-temperature systems, and binary plants expand usability. Policy incentives, feed-in tariffs, tax incentives, and renewable portfolio standards. Hybridization and integration, synergies with solar, hydrogen, and energy storage enhance value. Emerging markets and opportunities. 1. Africa. Kenya, Ethiopia, Djibouti, Rwanda, and Uganda have high geothermal potential. Growing international investment and regional cooperation. 2. Latin America. Mexico, Chile, and Bolivia exploring high-enthalpy resources along the Andes. Geothermal energy supports mining and rural electrification. 3. Asia Pacific. Indonesia and Philippines, leading in installed capacity. Japan, India, and New Zealand, expanding exploration. 4. Europe. Focused on direct use and low-temperature applications. Germany, France, Italy, and the Netherlands, investing in deep geothermal and heat networks. Technological trends shaping the future. 1. Enhanced geothermal systems, EGS. Unlock geothermal energy in areas without natural hydrothermal systems. Countries like the USA, Australia, and the UK investing in EGS pilots. 2. Supercritical geothermal. Tapping extremely high temperature resources greater than 400 degrees Celsius promises 5 to 10 times energy output. Research underway in Iceland and Italy. 3. Hybrid systems. Integration with solar PV, biomass, and hydrogen production. Improves efficiency and load balancing. 4. AI and digitalization. Used in resource modeling, exploration, real-time monitoring, and predictive maintenance. Reduces exploration costs and enhances performance. Challenges to market expansion. High exploration risk and costs. Limited awareness and expertise. Slow policy and regulatory development. Access to financing in developing economies. Environmental and social licensing issues. The role of international cooperation. Global Geothermal Alliance, GGA, platform under IRENA promoting geothermal development. World Bank, IADB, AFDB, provide funding, technical assistance, and policy support. Partnerships between governments, private sector, and research institutions to share knowledge and reduce costs. Future outlook. Projected capacity growth. Global geothermal power capacity could reach 30 to 35 gigawatts by 2035. Direct use is expected to grow even faster due to urban heating and agricultural demand. decentralized systems, increased use of modular and small-scale geothermal systems in rural or off-grid areas. Geothermal in net zero strategies, seen as critical for baseload power and heating decarbonization in climate plans. Conclusion: geothermal energy stands at a pivotal point in the global energy transition. Its unique advantages, such as high reliability, 24/7 availability, and a small carbon footprint, make it a powerful complement to solar and wind. While challenges remain, advances in technology, supportive policies, and international collaboration are paving the way for a brighter geothermal future.